All right, Boston Spa, it's time for a new unit. Today we're going to start modern physics. And like most days in Regents physics, you should get out your notebook, pencil, reference table, and calculator and have it with you as you take notes because we're going to need the reference table for at least three different things today. So gather all those materials and let's get after it. Modern physics is in quotes because when I say modern, you're probably thinking, okay, maybe this is stuff that was developed last month or last week or last year. It turns out that modern physics is everything after 1900. 1900 is when Mr. Einstein did some of his major work, and Max Planck is also involved. And you may have heard the term quantum mechanics. Modern physics is often known as quantum mechanics. If you've ever seen some kind of a special on the Science Channel or the Discovery Channel, you may have heard the term quantum mechanics. So, what's so different about it? Why do we need it? Well, it turns out right around 1900, humans, the history of scientific innovation has been the history of being able to look closer and closer at matter. People originally thought there was just matter, and then there were atoms, and then there were electrons, protons, and neutrons. Well, as you start to look at the atom, you quickly figure out that it obeys a different set of rules than, let's say, your car or a thrown baseball. The equations that we've come up with so far this year, you can basically throw those away when you go to deal with the world of the atom. So we need a new branch of physics and a new set of equations in which to approach the world of the tiny, which is what quantum mechanics deals with. So, um, so basically, the problem occurs with light, or at least the problems begin with light. So the question is, so what is light? Like when you turn on a flashlight, what is the stuff that comes out of the flashlight? Well, up until 1900, people have been thinking of light as a wave. I mean, if you think of where we studied light, it was in the waves unit, um, electromagnetic radiation. And you may call things like diffraction. Diffraction is the bending of a wave around a barrier, and light diffracts quite nicely. So when you look at what light does, one would quickly deduce that it's a wave because it does all of the things classically that waves do. Well, right around 1900, people started running into a problem. There was something known as the photoelectric effect, where you can take light and shine it onto a metal, this little graphic in the lower right, and that light then disappears and kicks off the electrons and frees them from the metal. And it turns out, if you play with this phenomenon enough, you will quickly realize that this whole setup here, the result that happens, does not cannot be explained by thinking of light as a wave. One has to rather think of light as a billiard ball. Think about playing pool on a pool table. One ball comes in and one ball comes out. Um, so, despite the fact that for a long time people have been thinking, okay, light is a wave, it turns out that in some situations, especially 1900 and beyond, as we start looking at matter more closely, one starts to see that light begins to behave like a particle. And this is really very disturbing because we're talking a lot of physics history where people just assumed that light was a wave. Okay, so how do we solve the problem? Well, to solve the problem, this is where Mr. Einstein gets involved. He borrowed some ideas from a big name at the time, Mr. Max Planck. Mr. Max Planck had stated that energy has certain allowed and unallowed values. Now, this is, on its own, a very bizarre idea. When we think about energy, we would probably like to think that energy can be any number that you want it to be. Well, it turns out that's kind of true in our world, in the macro world, but when you shrink down into the world of the atom, it turns out that energy comes in chunks. It comes in certain values, and it has certain values that aren't allowed, which is kind of a weird concept in our world. If I were to tell you that, okay, you're driving down the street in your car, and you're not allowed to have any old kinetic energy that you want. Well, the way we think about it, if I just step on my gas pedal and go faster, I gain more kinetic energy. Ke is 1/2 mv squared, so if you raise your velocity, you will raise your kinetic energy. Well, you might think that you can have any energy you want, and that's true in our world, but when you shrink down to the world of the atom, it turns out there would be energies that are not allowed. So if we go to the next slide, in our world, here we have a turtle on an inclined plane. If you wanted to give this turtle some gravitational potential energy. As you may remember, gravitational potential energy is proportional to height. So if you change the turtle's height and make it higher, it should have more potential energy. Well, in our world, we like to think that we can put this turtle wherever we want to on the incline. If you want to give it more energy, you raise it higher, and if you want it to have less energy, you bring it down lower. And there's no reason to believe that you're not allowed to put it in any particular place, because that's the way our world works. Now, here in the world of the atom, this is a better way to look at it, that the turtle can only have certain energies. The turtle can be on these three stairs, and it can't be anywhere else. So the turtle would not allowed to be in between the stairs. It can only be on the stairs. And if you use this model, you can quickly see that energy would have certain allowed values, the red stairs, and it would have certain unallowed values, which would be in between the stairs. So quantities that behave like energy in the quantum world get a fancy name. They're called quantized. Any quantity that comes in certain values and has illegal values is said to be quantized, which is the opposite of continuous. When we think of the number line and numbers, we think of things that are continuous, but quantized means that they come in chunks. So we've already met one quantity this year, although we didn't use the word quantized. We met a quantity already that comes in certain chunks and has unallowed values. Hopefully you could think of what that is. Back in electricity, we learned that the elementary charge, um, the elementary charge comes in values of 1.6 times 10 to the negative 19th coulombs. And you can only have charges in this chunk. So your allowed charges are 1.6 times 10 to the negative 19 coulombs, 3.2 times 10 to the negative 19 coulombs, and so on. So a charge of 2.9 times 10 to the negative 19 coulombs would be unallowed. So electric charge is quantized, and now, wonder of all wonders, energy is a quantized quantity. Strange indeed. So let's put some numbers on things. Einstein comes along and says, all right, light then, if it's not going to behave like a wave, let's pretend it behaves like a little billiard ball, which will be a little tiny packet of energy. So Einstein comes along and puts this little word on light and says light is a stream of particles, and we'll call those particles photons. Not to be confused with protons that are inside the atom. This is photo as in light, photons. So photons are little tiny particles of light. It doesn't mean that they're not heavy. It means they're just tiny particles of light. They're not light particles. And of course, we need an equation. Einstein says that every single particle of light, every photon carries an amount of energy, energy photon, EP, equal to HF, where F is the frequency of light, which is going to be measured in hertz, right? We did all this back in waves. Isn't this bizarre? We're talking about the fact that light is not a wave, that it's a particle, yet we are using wave phenomenon in the equation to describe the particle of light energy. Yes, everything about modern physics is rather weird. So energy of the photon is h, which is Planck's constant, 6.63 times 10 to the negative 34 joule seconds. It's another one of our universal constants. It exists on the front page of the reference table. It's down near the bottom of the list of physical constants on the front page of the reference table. So why don't you take a moment to find that? And when you want to know the energy of a single particle of light, you multiply Planck's constant times the frequency of the light, and you will get an energy measured in, no surprise, joules. Although the electron volt is going to come back big time in this unit, for right now we're talking about the energy of a photon in joules. Well, what if someone gives us wavelength instead of frequency? Well, you may remember in the waves unit, when we talked about light, we took our old friend, we took our old friend V equals lambda F, and we made it C equals lambda F. So if we want to get rid of frequency, frequency will be the speed of light over the wavelength. So we can put C over lambda in for F, which would give us E equals hc over the wavelength lambda. If I were you, on your reference table, because this is the first equation on your reference table, if I were you, I would go ahead and write equals hc over lambda right after the E equals hf. Oh, well, I just glanced at the reference table. I forgot that is there these days. It's E equals hf equals hc over lambda. So this is on the reference table, and this is on the reference table, all in one string. If you look at the modern section of the reference table, which is not a very big section, if you take a it is right below the wave section, and there's only three equations there, and one of the equations happens to be E equals hf equals hc over lambda. Yes, curve shapes, they never go away. These two graphs, why don't you take a moment, pause the video, and sketch what you think the energy of the photon versus frequency and the energy of the photon versus wavelength would look like. All right, our equation that has E photon and F in it would be E photon equals HF. So if you take a look at those two variables and circle them, remember how this works. If they're both in the numerator and they're neither one, you don't have a squared or square root, then you're looking at a nice straight line. So you should have a proportional or a linear fit. And here we have energy of the photon versus wavelength. So the equation that goes with that relationship, E photon equals hc over lambda. Now if we circle the two things that are being graphed, energy of the photon versus wavelength. We've seen many times this year where y is in the numerator and x is in the denominator. Hopefully you remember what that looks like. That's our hyperbola. So that graph's going to look like that, asymptotic to both the x and y axes. All right, so what the heck is light? We've seen in the wave unit that it behaves like a wave, and we've seen in this unit that it's beginning to behave like a particle. So what is it anyway? Well, the answer is light behaves as both a particle and the wave, just really never at the same time. Depending on how you look at it, it can sometimes be a wave, and if you look at it a different way, it can be a particle. So when you do a diffraction study, you will quickly see that light will behave like a wave. And if you do things like collide electrons with other particles, as in the photoelectric effect, you will see that light behaves like a particle. So this dual behavior is known as particle-wave duality. I like this little graphic. If you read it, it looks like light is a wave, W-A-V-E, and also you can see light is a particle, P-A-R-T-I-C-L-E. So depending on how you look at the word on the bottom, you can see either wave or particle, which is just the way light behaves. Another picture that sometimes you'll see in psychology classes when discussing perception is the picture known as young woman, old woman. Here's the face of either a young woman or an old woman, depending on how you see it. So the old woman, here's like the black hair here up at the top. This is her chin. This little indentation is her mouth and her nose. And she's kind of looking off and to the left here. This is one of her eyes. This is the other eye. And the young woman is looking away from us. This is her little nose right here and her eyelash, and this would be an ear, and this is still her hair, but she's looking off to the distance in the left. And depending on how you look at it, you'll either see the young woman or the old woman, but you won't usually be able to see them at the same time. You can either see one or the other, which is just the way light works. All right, let's work an example. A photon has an energy of 2.11 electron volts. Yes, electron volts are back. If you remember, electron volts is a unit of energy, and it's convertible between joules and electron volts. Hopefully, you remember the conversion factor. It's waiting for you on the front page of your reference table. So if we want to convert, we know how to do that. We have to make a bracket. So we start with what we're given, 2.11 electron volts over 1. Now we need a new bracket. And in order to get the units to cancel, we have to have electron volts on the bottom and joules on the top. And now we have to put the conversion factor in. 1 electron volt, says the front page of your reference table, is 1.6 times 10 to the negative 19th joules. And if you multiply that out, you will get 3.376 times 10 to the negative 19th joules. So a single photon of whatever color this light is has an energy of 2.11 electron volts, which happens to be 3.376 times 10 to the negative 19th joules. All right, now we want to calculate the frequency of this light. So we have energy of the photon. We have energy of the photon right here. That goes in here. And we know Planck's constant. That's a universal number, front page of the reference table, and we can solve for F. So frequency would be energy of the photon, which will be 3.376 times 10 to the negative 19 joules over Planck's constant. So you're taking notes in your notebook. Let's fill this in. 3.376 times 10 to the negative 19th joules, all over 6.63, boy, I missed my smartboard, times 10 to the negative 34 joule seconds. Notice how the units work. We have joules over joule seconds, so the joules cancel, and we end up with 1 over seconds, and you may remember that that is the definition of hertz. So there's our hertz coming back. So the frequency of the light in this particular case is 5.09 times 10 to the 14 hertz. This is a great review of waves because this number should give you a little bit of comfort. Whenever you see times 10 to the 14, you know that it's gonna has a good chance of falling in the visible light spectrum. So do you remember how to look up the color of light? You go to the page on the reference table that has the electromagnetic spectrum, and we look up 5.09 times 10 to the 14 hertz, and that is yellow. So a yellow photon can have an energy of 2.11 electron volts, which is 3.376 times 10 to the negative 19 joules. All right, one more quick idea, and we're out of here. Compton scattering. Since light behaves like a particle, meaning a photon, it can be traveling along and collide with a physical particle, like an electron. So we might have an electron sitting here, and we might have a photon heading in, which sadly is drawn like a wave. Usually the picture of a photon would be like a little particle with a wave inside it because it behaves as both a particle and a wave. And then when you have the collision, every time that matter, electron, and energy, a photon, collide, both energy and momentum are conserved. So when this collision happens right here, energy will be conserved and momentum can be conserved. That's called Compton scattering. And I think you'll see when you do your multiple choice homework that somewhere in there, the Compton scattering, the fact that both energy and momentum being conserved shows up.